So okay, good day. So today we will have our fifth example for stresses and beams, specifically bending stresses. Okay, so we will have our next problem, which is 5.10. Okay, so a W250 by 28.4 A section is used as cantilever beam of length L is equal to 6 meter. Determine the largest uniformly distributed load uh, WO in addition to weight of the beam that can be carried if the bending stress is not to exceed 120 megapascal. Okay? See Appendix B2 for properties of the beam. Okay? So this will be our problem. Okay? So 5.10. So to me, okay? So we're gonna solve it. Okay? So I already have here the solution. Okay, so this is my solution. Okay, so when we say of cantilever beam, it means that it's one of its side is equivalent to um, one of its side is free and one of its side is fixed support. Okay, so this is the cantilever beam. One side is fixed support and the other side is free. Okay, so since we have W is equal to 250 by 28.4, so we will find it at appendix B2. Okay, so it can be seen actually in our book, in our PDF book by Paitel and Q. Salaas. Okay, Mechanics of Materials. Okay, so maybe let's try finding it. Okay. Okay. B2. Okay, so this is B3. So we start at B2. Okay. And we'll try to find 250 by 28.4. Okay, so this is B2, table B2. Okay, so we try to find W250 by 28.4. Okay, so 250 by 28.4. So this W250 by 28.4. So here it is. Okay, so we need to find several factors, or we can use several aspects in which we could use it to solve the unknown. Okay, so we will try to solve WO. Okay, so here before we compute the WO, we need to find its allowable moment. Okay, so here we need to find the S. Okay, so the S of W250, okay, by 28.4. Okay, so here is the S. It is equivalent to okay, where is the S? So here is the S. So which is the section modulus. So our section modulus by 28.4 is 308. Okay, so 308 by times 10 to the third to mm cube. So this is it. Okay, so that is why we have this one. Okay, W times 250, W250 by 28.4. When we say W, it is a wide flange beam, or it has a section like W shape. Okay, it is actually an I shape in which okay, so it is a wide flange beam. Okay, it looks like this. Okay, So the shape of a wide flange beam is like this. Okay, so this is it. Okay, so then we all know that we should not neglect the weight. So therefore, the largest uniform distributed load is WO and then additional of self-weight. So our self-weight is, since it means W250 by 28.4, so meaning the width is 250 and then the weight is 28.4 kilogram per meter. Okay, in order to compute the self-weight in terms of Newton, we multiply it by 9.81 Newton per 1 kilogram. Okay, so since 1 kilogram is equivalent to 9.81 Newton of force, so we multiply it. Okay, so we get 278.604 Newton per meter, or equivalent to 0.278604 Newton per mm. Okay, we use Newton per mm so that we will have a uniform units of Newton and millimeter as we go on with the next formula. Okay, so the next formula is here, W. Okay, so here, okay, so the maximum moment for cantilever beams is WL squared over 2. Okay, so we base it first. Okay, so it is actually given. Okay, so you need to memorize it. If it's for cantilever beams, its maximum moment is WL squared over 2. For if its loadings is uniformly distributed. Okay, for cantilever beams, okay, so this is actually cantilever beams. I would like to clarify, is for cantilever beams subjected to uniformly distributed load. So this is how it is. So if it is not, if the cantilever beam is not subjected to a uniformly distributed load, or if there is another load in which is a point load or triangular load, so we cannot use this formula. So it is only if in this case in which it is uniformly distributed load, its loadings. Okay, so since W is equal to WO plus 0.278604, so we substitute. Okay, so M is equal to WO plus 2.278604 L squared over 2. Okay, so from that we need to substitute that into this formula, and we all know that the, okay, from the given, should not exceed 120 megapascal. So therefore our maximum bending stress is 120 Newton per mm squared. And then so we substitute everything. So here it's actually 6 meters times 10 to the third. Okay, so we convert the length into millimeter so that it will have a uniform values, all Newton and mm values. So we get WO is 1.7747 Newton per mm. So we convert it into kilonewton meter by, okay, so we convert this value to kilonewton meter. So it will be the same. WO is 1.7747 kilonewton meter. Okay, so that is how we solve. Okay,